Uh, hey Akhilesh, hey Vishal. Uh, all right, so I think now is the right time to start. Cool. All right, so let's quickly get on with things. Um, Give me 1 second. Let me just quickly share my screen and then uh, let me just quickly set this up. All right. So a quick fact check. Is my screen visible and are you guys able to hear me properly? Okay, perfect. All right. Um, Thanks for letting me know. Right. So, uh, right again, good evening, everybody. Right. Today's session is going to be on solidity. Right. So we've had 3 sessions already. We started off on the very basic levels of discussing what Ethereum is all about. Right. We started looking at the architecture in more detail, and then went on to looking at Ethereum's clients, right? How do you manage those clients? How does a network get built up, right? How does that architecture actually manifest itself in the real world, right? So we looked at Geth as one example, right? We put our hands onto an actual Geth environment, set it up, ran some very basic commands, got a feel of what it is to run a Geth node. uh, so we will take it from there, right? Today we will move further into this journey of Ethereum. We are nearing the end of all there is to know about Ethereum. Obviously, there is a lot more to go out and read, right, and get much more information about. The idea for these sessions essentially is, again, like I said last time, right, is to expose you guys to all of the resources and a very broad overview of what's there, so that you can then go out and then you have the dots that you can connect and read more and get more sense, right? At the end of the day, this is programming, so the best knowledge is only going to come by you guys trying it yourself, right? So keep trying. The more trial and errors you make, the better you will get at doing these things, right? So that's the only real way that you're actually going to learn any programming. All right, so today's session on solidity, let's quickly discuss the agenda and then we will do a little recap about what we did yesterday. I know there's a question that's coming from Akhilesh about something related to last time. I have not read it yet, but we will address some of the questions that we might also have from last time as we do the recap, right? So let's first quickly go through the agenda and make sure we've put at least most of the things that we think we can cover. So one important thing about today's session, this is Solidity. It's a programming language, right? Uh, Obviously, nobody in the world is going to be able to learn a programming language in 2 hours. So the agenda for today is not going to be for you guys to learn and at the end. So the idea is not to make each of you guys Solidity experts by 10 p.m. today, right? The idea is to give you guys a sense of what it takes to build on Solidity, how similar it is to the other programming languages that you might have looked at, and how different is it. So we will look at the whole session. I mean, individually, all of you guys, I advise you to look at each of the slides or everything that we learn about Solidity and try and benchmark it with what you already know about different programming languages, right? Because the idea is we're not going to start from scratch, right? Obviously, we've all had some exposure to some, at least one programming language before. So this is going to be a delta, right? So focus on the deltas as more than trying to get to the root of every single term that you come across today, right? That ways you will feel more comfortable accepting the fact that Solidity is a fairly similar programming language versus some of the other ones that you already know, right? And then you can then go out and read through all of the Solidity docs and actually try out some of the examples to get a very, very detailed understanding. All right. um, so the agenda will have sorry about that. We put this on silent. Okay, so the agenda is going to have defining what smart contracts are. We will be talking about the life cycle of smart contracts, the development environment, right? And then we will go deep into solidity, the data types, what are the different global variables available, different built-in functions that are available. How do you build contracts? What are the different modules that go inside of a smart contract, right? All of the different parts that add up to building a smart contract. And towards the end of this, something that's actually not listed in the agenda, but I hope we can probably touch towards the end of the session, is also talk about web3.js, right? Which is the other part of building contracts, is to actually consume those contracts through applications, right? So the idea is we finish up Solidity on a very broad level today, briefly cover web3.js, and then we continue with web3.js in the next session, which will be the last session for Ethereum. And use that knowledge to build our first smart contracts and an application that consumes those smart contracts. All right. So does that look good? All right. Yes, Kishore. Why are we learning Solidity? That's a very good question, and I think the first few slides will sort of explain as to why we're going to be learning Solidity, right? Obviously, it is important if you want to do anything on Ethereum, and that's why it's the most convenient methods of doing or building applications on top of Ethereum. All right, so let's now also do a quick recap about what we've learned last time, right? We'll swiftly drift through the recap because actually there's a lot to learn about today and a lot to look at today. Solidity is fairly vast. Obviously, it's a programming language of its own, right? But let me also look at some of the questions that have come in, right? Akhilesh has asked, can you please provide the correct command to install get on Ubuntu 18.04? Right. So for installing get on Ubuntu, Akhilesh, the commands I think are already mentioned inside of that Word doc that I shared, right? Which should be a fairly straightforward process. I think there's only two parts to it. One is to link to the repo for Ethereum, right? So you would have to first install some of the supporting libraries, do a get update, right? Do an apt-get update, and then just tap into the repo for Ethereum, and then finally do an apt-get install for Ethereum. That should do it. I think those 3 or 4 steps are listed in that Word doc. If you don't find it, let me know. I'll towards the end of the session, I'll see and update it. Okay. All right. So if it's not working, Akhilesh, then all right. If you've given it enough tries, then I think we would have to go into a debugging mode, right? So share some logs of what's not working, on maybe we can do this offline, right? So send me an email about what's not working, and maybe I can help you with that, right? But before you send me something, make sure you've spent at least 3 hours on it, right? Because otherwise it's just too easy. All right. Okay. So let's do a quick recap. I think there's one other question from Akhilesh again. Are same smart contracts used in Bitcoin? No. Right. So Bitcoin, it doesn't really have the concept of smart contracts, right? Bitcoin's, network is essentially just built on transactions, right? So you can't really do a lot of processing or logic on Bitcoin, right? We've looked at this while we were studying Bitcoin, and we know now that Bitcoin is essentially, just an alternate for payments, right? It's a network that's built just for payments. It doesn't have the whole logic and processing capabilities that Ethereum has, right? So you can't build there is no concept of a smart contract on Bitcoin. All right. Okay. So let's quickly do a recap. So what are the main Ethereum networks that we've looked at? Right. When I say networks, I mean the chains, right? What are the main chains that are currently active in Ethereum? Right. Frontier, right? That's the main chain. Right. Rinkeby. Yeah. So it's spelled as Rinkeby. Uh, right. Uh, Robston. Yes. Uh, so Rinkeby and Robston and Frontier are the three most popular chains that are currently available inside of the Ethereum network. Uh, Vinay is asking, in the last session, we all created a network with ID 2019. Why didn't we all sync up? So it doesn't work like that, Vinay, right? So just because we created a chain in our local network with ID 2019 uh, does not allow other people. So, like, remember I said earlier when we were talking about decentralization as a concept, wherein I think there was session 1 or 2, right? We were discussing about the idea, and I said that one of the things that make decentralization so complex is node discovery, right? Is to figure out who else are available on that same network, right? And then to be able to discover those nodes, find the right communication language that both understand, right? Set up that communication and then exchange information to join the network, right? So that whole node discovery process is something which bootstraps a network, right? Which if you're joining the main chain, right, it happens automatically because it's sort of hard coded inside of the EVM machine. But if you're creating a private chain, that does not exist, right? So you have to each of the guys, if we were to sort of come down to a same network, we would have had to set up that whole communication process between our machines, right? Which is fairly complicated, but that has to be done. Unless, so you can't, so nodes just don't randomly discover who else suddenly come onto a network. That's not how it works. All right. Sure, Gokul. Not a problem if you have to leave. Sure, if you can look at the session, and then if you've got questions, you can share it. All right. Uh, Yeah, yes, Vinay. So Vinay has been asking, so network IDs 1, 2, 3, 4 are hard coded to connect to, not connect to the public network. Yeah, I mean, obviously all of those networks are public, yes, but they are hard coded in the sense that if the ID is 1, then the EVM instance knows, where or which particular IP addresses to go and look for, so that it can find the peers to connect to. Right. Similarly, if the ID is 3, then it knows which are the base peers to connect to so that it can find the other peers. So the whole network discovery process is hard coded, for the specific chain IDs that we're talking about, right? At least the ones that are popular. Uh, and the way it's hard coded is it's not hard coded inside of the code itself. It's actually hard code. So there's a file, right? There's a node discovery file. It's a config file that's part of the EVM binaries, and so there are those pre-populated files available for these networks that are popular, right? So if we have to build our own network, we have to basically build a network discovery configuration, and then our network can then allow other people to sort of self sub. So all of the other people will need to know what are these core peers that are always available, which is where we first connect, and then they let us know about all the other people, all the other peers in the distributed network, and that's how you discover more and more peers in the network. uh, you know so it's with Ethereum, it's sort of a little, the process is a little more complicated because then it's a it's a pure permissionless network, and people don't really set up private Ethereum chains as much as they would do for the permission networks, right? So when we start looking at the permission networks like Hyperledger, right, I think starting next week or something, uh, that is when this whole discovery process will become a little more clearer, because within Hyperledger we're actually going to connect multiple nodes together, right? And there you will also be looking at how these nodes sort of talk to each other. We'll look at some of the logs that will give you a more detailed sense of what it takes for these nodes to talk to each other and discover who else are available on the network. All right, so let's quickly get back to this. The next question that we have is, which are some popular Ethereum clients, right? And why are there multiple Ethereum clients? Right. So correct, right? Geth, Parity, CPP Ethereum, Pi Ethereum are some of the most popular Ethereum clients. Geth and Parity are the most popular. I think Geth probably number 1, Parity number 2 in terms of their usage currently. And the reason why there is multiple clients is we've looked at this last time, right? We know that this is because the Ethereum developers wanted a way to keep the protocol, the developers honest, the protocol robust, right? And to make sure that all of the issues are rooted out, because there are multiple people developing clients on the same protocol, right? So those are some of the reasons why they chose to have multiple client implementations. Right. So which are the APIs that are available in Get to run and manage a particular client? Right. Personal is one such API. Yes. There is admin. Yes. There is init. Init is a command. Init is not really a set of APIs. Init is a command that we use to to create that Genesis block. Right. Web3 is a set of APIs. Um, yeah, so these are some of the main APIs, right? We have TX pool, which is a transaction pool API, and yeah, I think these sort of cover most of the ones, right? Miner is one of the other APIs, right? uh, uh, right. I think there was a question that had come in from Suresh, right? He said, can we open another terminal and attach and create a new account so that you can sync? That is correct, but that still is a node discovery. So what's happening there, and that was something that we intended to do as part of last session, was we created a get node, we created an account on it, and then the plan was to open up another get node on the same computer, and then attach both of those get nodes together, right? But that would not have been through automatic discovery or any sort of syncing. The way that would have worked is we would have got the IP address for node 1 and then put that into node 2 to connect to node 1, right? So you would have explicitly connected both the nodes together on the same network. All right. So question 4 is, which address does the Ether rewards go to? I think Suresh sort of already put that in, right? Coinbase, correct, right? So the Coinbase address is where the Ether rewards go to. We've seen how you can set the Coinbase address. We know that by default it sets to the first address inside of every node, but you can change that using the APIs that are available, and you can set it to some other address. There can only be one address, which is the Coinbase address for every node. And then how do you control the mining process inside of an Ethereum client, right? What sort of commands do you use? What sort of options do you have in terms of like controlling the mining process? Correct, right? So there's miner start, stop. You can look at some of the statistics, through some of the other miner commands, right? Within start, you can put in the number of core CPUs, virtual CPUs that you want to use, or the process threads that you want to use, in terms of resources available to mine. Right. So those are some of the important things that we looked at last time, right? We will quickly now move on to, our plan for today. That's Solidity, smart contracts in detail. All right. All right. It might seem that I'm swifting through swifting through some of the slides quickly, but don't worry. These slides aren't necessarily meant to be covered one by one, right? Because these are a lot of slides, about 97 slides that I have in total for just covering up Solidity. So obviously we're not going to be going through all of the slides, right? I will be swifting through the slides to cover up the most important parts, right? So try and focus more on the more important terms that I talk about instead of reading through each of the slides. And that way you will not sort of feel bored essentially. All right, because this is programming, right? We're going to be learning a lot of theory of programming. So try and stick with me. All right, so we've looked at the history of smart contracts. Again, some very basic information about the idea of smart contracts. I think most of us are fairly familiar with the idea of what smart contracts is now, right? We know that in terms of blockchain, smart contracts are essentially some sort of decentralized code, right, that you can put on top of a blockchain platform. And they the concept of smart contracts have existed, long back. But one thing to remember is these smart contracts, right? The word contract has no legal meaning, right? There's simply software programs, there's simply computer programs. So there's no legal meaning to the idea of a smart contract, right? Also, the smart contracts are immutable. So once you've deployed a smart contract onto a blockchain, you cannot change it, right? Traditional software is if you've made mistakes or your software updates, you can put those in, and then people will be able to enjoy a new version of the code. But that doesn't happen with smart contracts, right? When smart contracts have to update, they have to deploy a new contract. All of the smart contracts are deterministic, right? Determinism is a property that, given the same environment, right? And in this case, when I say the same environment, I mean the same context, of execution. As long as the input is the same, the output will always be the same, no matter who uses it, right? So that's determinism in terms of computer science, right? It's a very simple concept, but it's very important for having machines that are used for critical purposes, which means that whether it was yesterday or 5 years from now, whether you use it or I use it, right? Whether it's operated here in India or somewhere in the US, right? No matter as long as the input parameters or the state of the machine is the same as it was, no matter who uses it or where it's used, the input and its dependency on the output, right? Basically, what output you get for the particular input will always be the same for everybody. Another important point for smart contracts is to remember that smart contracts operate on a very limited execution context, right? I've been saying the word context. I'm not sure if most people are aware of what a context is, right? So just to get you a sense of what a context means, in a computer, in a computer programming sense, a context is essentially, so let's look at from a very generic sense, right? So today, if you guys are asking me questions, for example, if Suresh had just asked me a question about, how do you connect with these nodes, right? The context that I had about the question was the fact that Suresh had come to the last lecture, right? That we had learned something in the last lecture, and the question is sort of a follow-up of what was done in the last lecture, right? So that's a context that I have apart from the question itself, right? Similarly, when certain operations are running inside of computing machines, these machines have some context about the transaction, right? So when you say that add, 1 plus 1, the machine might have some other context about the transaction, which could be things like, that this transaction was received at this particular timestamp, right? Or for example, we could have some sort of, information about 1 plus 1, the plus function, right? This is what the plus function does, right? Or things like, this is the guy who's asking for 1 plus 1, and when he asks for 1 plus 1, this is what he expects out of his. So there are certain contexts that the machine has about an incoming transaction. On your regular computers, the context that your machines operate in, right, are all of the hardware that is available to that software program, all of the network resources that are available, right? The whole information. So if the software program connects to the internet, then it has the context of the whole World Wide Web, things like that, right? So a context is essentially, information that your software has that it can probably utilize as part of running the code, or you as developer can utilize as part of writing your code programs. For EVMs, what we are saying is, for your smart contracts operate in a very limited execution context, right? So basically what we're saying is your smart contracts have no access to, your local machine, right? They have no access to any of the hardware on the machine. They have no access to the internet, nothing, right? So they have very limited access, and some of that access. So we'll be looking at what sort of execution context they live in, right? And that is why, they have limits on what can be actually put inside of those smart contracts, right? And how you code them. Finally, obviously, we know that, these smart contracts run on an EVM instance, which forms the Ethereum blockchain, right? And although they run individually on individual nodes, they all share that same network state, right? Which is formed through the blockchains, the blocks forming one after the other, and then the transactions linked to another. So they all have access to that same state, which means for everybody, X is the same value 1, Y is the same value 0. right? And so in a sense, they all operate like a single world computer. All right. So some of the highlights of smart contracts, right? So again, these highlights are not meant to be completely understood right now. They're just an overview of what's to come in more detail as we go forward, right? So so these are like points to note. All right. Smart contracts are typically written in high level languages like Solidity, right? That's so although your machines, or your Ethereum virtual machines will not execute these smart contracts in the same language, but they're written in a high level language like Solidity, and then it's compiled down to a lower level bytecode, right, which is what the EVMs run on. We will be looking at what EVMs are in much more detail, right? But think of it like an operating system like Windows, right? So it's a virtual machine that runs on top of your machine, which is your OS, and that is where the whole the whole code, or the smart contract code, is essentially executed every time you have a transaction coming in. All right. The other thing to remember is these smart contracts, we've talked about this. There is a contract creation transaction that can happen, right? A contract creation transaction is essentially a special transaction which is sent to an address which is all zeros, right? 0x00. And when you send a transaction to that address with the contract code inside of it, right, it's considered as a contract creation address, contract creation transaction, and a new smart contract is created out of that. Every smart contract is associated with an address. We know that contracts are essentially contract accounts, right? And they have an address, a 20-byte address, right? And the value attached to it. The value is where the storage is, and the inside of the storage is where you have the code. We also know that contracts only run if they're called by a transaction, right? So there needs to be a transaction that needs to trigger a contract. Otherwise, they cannot just run on their own. Contracts do not run in the background, right? This is very important, right? So you cannot, like your processes on your mobile phones or your computers, right? You cannot have a contract run in the background. So a contract will only run when you have an input transaction. It will run for the duration of the transaction. It will return a result, and then it will stop running, right? So the only time it will run next is when a new transaction comes in. There is no such process as running in the background. Right. So the other thing, we also know that all of the transactions are only initiated by externally owned accounts, right? Contract accounts can only be triggered by externally owned accounts, or they can also be triggered by other contract accounts. But those contract accounts first have to be triggered by an externally owned account, right? So the start always has to be from an externally owned account, and then if an EOA initiates a transaction on a contract account, that contract account can then reach out to other contract accounts. All right. The other thing we need to remember is the whole smart contract execution process is a single threaded machine. There is no concept of parallel processing, right? So it's synchronous. All of the transactions are executed, in a tightly coupled one after the other process, right? One after the other sequence. The transactions are atomic. The concept of atomicity is, if a transaction is run and there are 5 instructions in part of the code, unless all 5 are successfully completed, the transaction, the state for any of these will not change, right? So what I mean is, a transaction is successful if all of the instructions inside of it have been successful. Even if one instruction fails, all of the others will be reverted back to their original state. Okay. So that's called atomicity. Also, remember that transactions operate in their entirety, right? And this is what I was just explaining, is the fact that if there is a change of state as part of the smart contract, if you have to change your state 5 times, right? And even if one of those instances fail, the entire smart contract will be reverted back. So either it operates in entirety, or it doesn't operate at all. All right. So Kishore has a question. Besides the slides in the live session, what is the source of the information? So all of this, Kishore, is publicly available, right? All of this information, the best source of reading everything that you want to learn about Solidity are the docs, right? So the Solidity docs are very, very well documented, very easy to understand. and I think those have been written very well in terms of helping a regular person. As long as you understand basics of code, you will be able to read through it and understand. All right. We've looked at the idea that contracts cannot be changed, right? They can be deleted, but they cannot be changed. All right. We will look at how you delete smart contracts. It's done through a process called self-destruct, right? Self-destruct is one of the opcodes. Again, we will be looking at what opcodes are, right? But one of the EVM opcodes is a self-destruct opcode that lets you delete a smart contract, but you cannot change them. Logs are generated by smart contracts. We've looked at that last week. In the previous session, we looked at how logs are generated, and what are the purpose of those logs. So in response to events, logs are generated by the smart contract. They're stored inside of the blockchain, and they can be accessed by other nodes, to fetch certain instructions that have happened as part of executing those smart contracts. Once a log has been generated, remember your transactions have no access to the logs, right? Outside users, people outside the blockchain can fetch those logs and look at what happened inside of the transaction. But if you're doing a future transaction and you think you can fetch data from one of the logs of the previous transaction, that's not possible, right? This is one of the things when we say that transactions operate in limited context, right? They don't have the context of the logs that are saved inside of the blocks. All right. So basically, what we have looked at is some of the highlights of smart contract. Right now, let's look at some of the high-level languages. Right. So basically, what we're saying is the EVM, which is basically the Ethereum virtual machine, is a machine that runs on something called EVM bytecode. Right. This EVM bytecode is like an assembly level code, which is similar to what your CPUs run on, right? But we code in the high level programming languages like Python, C, C++, right? But then it eventually compiles into a bytecode language, which is what your CPUs understand. So similarly, the EVM virtual machine runs on these bytecodes. And when you code in Solidity, it eventually compiles down to the bytecode. All right. Obviously, you could have just coded in bytecode, but it's very difficult, and that's why nobody does that. Also, remember that smart contracts cost you money, right? Every time you execute a smart contract, there is the concept of gas, which we have looked at. So you spend gas, and that gas is essentially some amount of ether, which is some real money, right? So if there are bugs in your smart contracts, it will cost you, right? And that's why it is always very important that you test out your smart contracts so that you can weed out those bugs before you make your projects live. Right, and that is why your languages need to be declarative, like Python style languages, which are declarative. Essentially, it's declarative is a way of the syntaxing of the language, which tells it's different from imperative languages, wherein you essentially code your languages talking about what you want to do versus how you want to do it, right? If you want to look at the concept of what declarative is versus different types of programming language syntaxing, Wikipedia is your best resource, right? But what we want to make clear here is, because mistakes will cost you money, it's important to code in a programming language that avoids or at least weeds out most of the errors that could have happened at the compiling level itself, right? So that once the code has gone live, it doesn't lead to bugs that could have been taken out at the time of compilation. All right. So there are multiple high-level languages built on top of the Ethereum bytecode, right? The EVM bytecode. As you can see, right, on my computer, LLL, Serpent, Solidity, Viper, Bamboo, there are multiple such languages that were built on top of the bytecode, right? But Solidity happens to be the most popular one. It's also supposed to be the one that's the best supported by the Ethereum development team. And it's also the most widely used, right? So the support for Solidity is much better than any other language. Viper is now picking up, right? It's a recently developed language. It's got a Python like syntax, so it's more easier to write, plus it's also more there's a lesser learning curve to Viper if you were to get into it, but it's still, the support is not as big as Solidity. Also, it's a recently developing language, so it's not gone to the level of stability as Solidity has, right? But do keep a lookout for Viper also in the future. All right. So this is where we answer one of the questions that was asked before, right? Why are smart contracts required, right? So why do we want to learn about smart contracts? Why do we want to learn about Solidity, right? So the idea is very simple, right? The idea is Bitcoin was one such blockchain which is built for a very specific purpose, right? Which is to be an alternative to money. But it shouldn't be the case in the world where for every specific purpose somebody has to build out a new blockchain. It's a very expensive, very, very complicated process to actually build your own blockchain, and then even more complicated to actually deploy it, right? It's a combination of several different departments of computer science coming together, and it's also very expensive. So you don't want to be in a situation where you have to build individual networks for every single use case, right? And that's why the idea of having a single network which acts like a world computer, where you can solve all of your use cases by building applications on top of that network, was born. And to do that, smart contract was the term designed for writing applications that rely or essentially reside on top of these distributed environments. Okay, so smart contract is just a piece of code that's running on thousands or maybe even millions of machines together, right? But the idea is, while it's running independently on each of those thousands and millions of machines, there are two things that are same. One, the code itself is the exact same. And two, each of those 1,000 instances or the million instances of your code that are running independently are sharing the same state. So because they're deterministic and the code is the same, right? Given the input, the output for each of those 1,000 instances will be the exact same, right? And that is the idea behind, when we say that smart contracts or decentralization brings together the idea of a world computer. Right. You guys have already looked at a lot of use cases, right? We've been reading about so much of this, and we know that there are so many use cases coming up, right? So smart contracts can be employed to use with a lot of different areas, everything from the government to, employment, or I don't even want to start getting into that industry space where, there are so many different use cases. All right. So the Ethereum virtual machine, let's look at that in a little more detail, right? It's called EVM. The full form is Ethereum virtual machine. The name sort of speaks for itself. It is a virtual machine. It is a runtime environment within which the smart contracts essentially run. Like I said, it runs in a limited context, right? So what that means is the EVM itself it's not only sandboxed. When I say sandboxed, it means that, it doesn't use the file system of your local machine. It doesn't use, the network of your local machine. It doesn't use any of the other hardwares except the CPU of your local machine. And even there, right, the memory space or the space that it operates in, right, as part of the CPU process, is completely sandboxed, right? So it doesn't interact or interfere with your base operating system in any sense. All it does is takes some of your computing resources and uses them for its processes, right? But otherwise it's a completely sandboxed and completely isolated environment that it runs in. And that is important because you want that level of security if you're working in if you're trying to create something that Ethereum has created, right? They also have limited access to other smart contracts, right? So every smart contract is essentially able to access everything inside of its own code, but there is some level of access available to other smart contracts, right? But it's limited, right? And we will talk about what level of access is available for a smart contract to contact or get details from other smart contracts. All right, we have already talked about the idea that EVMs are frequently updated by the process of EIPs, right? And we know that the latest one is called St. Petersburg, right? The one before that was called Constantinople. So EIPs, or the Ethereum Improvement Proposals, lead to some new code that is designed, some new code that is added to the EVM repository, and time to time they will release a new version of EVM that is updated on all of the machines that are running on the Ethereum network. All right. So there are three memory areas that so this is a fairly important thing to understand, because if you're working with Ethereum and you know that this is every transaction will cost you money, right? It's good to have at least a very top level understanding of where data is stored, right? Because some sort of data storages inside of Ethereum will cost you more versus the others. Okay, so what you need to know is the EVM essentially operates like a stack. It's a stack machine, right? Which is basically, a first in, first out, last in, first out sort of a stack. Again, you don't need to go into the basics of how stack machines work, but the idea to understand is there are three important storage areas. Okay, three different types of storages available for the whole EVM virtual machine, right? The first one is called the storage itself. This is the only storage which is persistent, right? Persistent means, it's a storage that, if the EVM is turned off and turned on again, right, the data inside of that storage will be available. It'll not go away, right? So it's like a hard disk, right? So this is the persistent storage which is available. It's called storage. It's part of the code account, right? It's part of the contract account. Remember, inside of the contract account, we had something called a code hash and then a storage hash. The storage is part of that contract account that inside of which we put the smart contract, right? That is a persistent storage. In the diagram, you might see the persistent storage being shown here, right? It's RAM, but it's actually NVRAM, right? Non-volatile RAM. All right. The second storage that is available to the EVM is called the memory, right? The memory is basically like a RAM that you have for your computers, right? It's where it will, memory is basically a volatile memory that it uses as part of its execution. That is where your local variables that you define as part of your code, right? Everything that you don't want to persist as part of your code, all of those state variables will stay inside of the memory, right? The memory will refresh every time a new transaction comes in. For every transaction, there is a fresh memory available. All right. So the other thing to remember is reading and writing to the memory will also cost you, and the memory grows quadratically. What that means is, if the memory grows in size, the cost of that will not grow linearly; it will go exponentially, right? Basically quadratically, right? So the larger the memory of your transaction or the memory consumption of your transaction, the more higher the price, right? So you need to limit memory consumption. And then finally, the third area that is available, the third storage area that's available, data store essentially for your EVM, is called the stack, right? The stack is where it essentially puts all of the data for computation, right? The stack is what operates in a last in first out method. So in this diagram that you're seeing on my screen, it'll give you a basic idea of how stacks work, at least the last in first out stacks, right? What that means is, I have an empty stack here, right? I add a 98 number on top of this stack, and then I add a 12 on top of this stack, and then I add another 45 on top of this stack, right? So now if I want to run, if I want to run an addition function, right, I'm going to tell the stack that take 45 and 12, which are the top two entries in the stack, add them, right? And then it replaces 57, which is the sum of that result on the top of the stack, right? So that's how stacks work, right? Stacks can only work with the top 15 entries on the top of the stack, right? So if you want to work with any data that's towards the end, you have to swap it out with the top 15 entries and then work with that data, and then it will eventually get pushed down. Again, it's a concept of, it's a computing concept. It's a very old concept, not a blockchain concept, right? But the only thing you need to remember is the stack size of Ethereum is 1024. So at max, you can have 1024 values put on top of a stack for every transaction. This is important because this will happen very frequently, that as you're building applications, if you write a function that's very complicated, right, and your transaction is trying to do a very complicated process on Ethereum, right, it will run out of stack space, right, and it'll overflow, right, and you will get an error. That's because only 1024 entries can be stacked on top of the EVM stack, right, and that cannot be extended. But that's for each transaction, right, and that is why it is important to keep your transactions and the logic behind every transaction as least as possible, so that one, less gas is consumed, and two, you don't risk the possibility of overflowing the stack. All right. Also, another thing to keep in mind is every time you put something on the stack, right, like you see on this little diagram here, the 98 number, right, it's called a word that is put on a stack, right. Imagine these words to be like, if you're playing something like any game where when you're stacking something on top of the other, right, every new item or a new element that you put on a stack is called a word. Okay. And the size of the word is basically how wide your stack is. All right. So in Ethereum, the size of the word maximum size is 256 bit. And that is why, as we go forward now, right, you will see that that's the limit of, most of the data types that are available inside of Ethereum, right? Because the stack size is 256 bit, most of your data types will be limited to 256 bits. All right. So now, no, this is, Suresh, this is last in, first out, right? Not first in, first out. So the last in is the first out, right? A first in, first out will have an exit from the bottom. All right. So let's continue now. We're looking at, so now let's start looking at Solidity, right? We've understood the idea of smart contracts, right? We've understood some of the highlights of how smart contracts should be working. We've also looked at, EVM in detail as to, how the whole EVM virtual machine works. It operates on bytecodes, but it's difficult to code in bytecode. So these high-level languages are built to code on top of EVM. We also looked at Solidity as being one of the various other high-level languages that are built to work on EVM. But because it's more popular, it is the one that we're going to be learning and playing with as we build our own smart contract on Ethereum. All right. So a little history. It was created by somebody called Gavin Wood. The main product of Solidity is essentially, obviously, it's the Solidity compiler, right? Also called Sol-C. Right, so Sol-C is the main product. So when we say Solidity as a product, we will most likely be referring to Sol-C as the compiler. All right, the version of Solidity, right, or the version of the compiler, which is Sol-C, plays a crucial role in deciding how you want to build your contracts. And the reason for that is Solidity is a very fastly growing language, right? So there are a lot of breaking changes that are introduced as part of every new version, or at least the major versions, right? So you might be using an older version of Solidity, or you might be using a newer version of Solidity, which no longer supports some of the code that you might have copy pasted from somewhere on the internet, right? So when you're working with Solidity and you're referring to some of the websites and copying code from there as part of your trial and error process, make sure you're looking at the fact that the code, right, is supported, or that particular line of code, wherever you're getting the error, is still supported in the new version of Solidity that you will be using. All right. So like I said, Solidity is compiled and the compiler is called Sol-C, right? It's compiled down to the bytecode language. There are various ways through which you can use Solidity, right? Or the Solidity compiler, which is Sol-C. Remix ID is one of the most popular ways of using Solidity. It's a browser-based, online development environment. It's also built by the Ethereum Foundation. So they prefer people learning and testing out Solidity on Remix. It's not something that you would use in the production environment, but if you're just building up, building smart contracts, it's one of the best areas to write your code and test it out. You can obviously install the Solc package through any package managers like Node, or Brew on your Mac machines, right? Or apt-get, or any other binary packages on your Linux machines. There is also a Docker instance available with Solc installed inside of it. So if you want to run it through Docker, that's also possible. People can also use frameworks like Truffle. We will be looking at Truffle towards the end of this session, which is a framework to build smart contracts, on top of Ethereum. All right. So now let's get to the code, right? We've looked at the basic introductions. We will now get into understanding how Solidity basically works, right? So Solidity is obviously used to define a smart contract, right? You will be coding your smart contract in the language called Solidity, right? So as part of a smart contract, let's first look at its structure, right? The structure of the smart contract is basically just this simple two things, right? You will have at the top of the file, so every single file is a smart contract on its own, right? It's a Solidity file. It ends with a .sol extension, okay, .sol extension. And the file itself will have one or more pragma directives or import directives. What are pragma directives? We will talk about that. Right? Import directives, if you've used languages like Java or any other languages which support inheritance, import is a way of, importing code written in some other file and then, inheriting it as part of your existing code. Right? So you can import other sol files inside of your existing files using import directives, or and also towards the very beginning of your sol files, you will be entering the pragma directives. Okay, pragma directive is basically a concept which is where you see towards the end of my slide here. So when I say something like pragma space Solidity space some version, what I'm telling the Solc compiler is, when you compile this code, right, remember that my code is built for a compiler version which is at least 0.5.2. And this little hyphen here, this little tilde here, it tells the compiler that, the version breaks, my support breaks at anything above 0.6, right? Which is a mid-level upgrade, the middle number, right? So this little thing means that, compile for the compiler version of 0.5.2 at least, right? And do not support anything above 0.6. You can put multiple things here, right? You can put pragma Solidity greater than 0.4.0, less than 0.5. Essentially, it is a way of telling the compiler that this is what your code supports. Yeah, Kishore, what happened? No, Kishore. So that's what I'm saying, right? Because it's a frequently updated language and they're bringing in a lot of changes. Also, the whole Ethereum network itself is changing frequently, right? So newer versions bring in breaking changes, right? Which means not backwards compatible. Right, so there will be new things that will come on, which will not. So those new versions will not. So for example, there have been at least 20 things that have changed as part of 0.4 versions and 0.5. Right, like for example, when we deployed our code, I think a year and a half back, it was running on 0.4.22. And when we had to update something and then we had to push it out like about 6 months back or something, the new versions at that point was I think 0.5.0, which is when 5.0 had just come, right? And we had to literally rewrite almost 40% of our code, right? So it's there are a lot of breaking changes that come in, at least the mid versions, right? The bigger upgrades. So the 0.5 version right now, the updated version is 0.5.9. So 0.5.0 to 5.9 have just been all supported changes and no breaking changes. But when 0.6.0 comes in at some point, that's again guaranteed to bring in some breaking changes. All right. So basically what we've looked at is the contract file itself will have this pragma directive at the top. It'll have some of the import directives to import some of the other sol files, right? And then it'll basically have one or more contract definitions, right? So within the same contract file, you can have multiple contract definitions, okay? Now, what is a contract definition? A contract definition is basically, it's just similar to a class in any object-oriented language, right? That you must have seen, right? So just how you define classes in object-oriented languages, you will define a contract class, right? And the contract class within itself will have one of these many things that, is listed down here, right? So it will have state variables, which are basically variables. We call them state variables because they are the states that are saved on top of the Ethereum storage, right? So the state variables, it will have functions. Obviously every classes have functions, right? It has a new thing called function modifiers, which we will be looking at. It's a very simple concept, but it's something that's specific to Solidity, right? So there's something called function modifiers, right? It will have events. We've looked at the idea of events. We know that smart contracts can trigger events which will cause logs to be generated, right? And then it has two different types, specific types that were created for Solidity, which was structs and enums, right? We know what enums are, right? Generally from programming languages, we know enums are enumerators, right? You can create a list with 5 options and, that becomes a type of data, right? For example, I can have an enum for colors, right? And inside my array of colors, I can define the 12 colors and that becomes my color enum, right? So enums are enumerators. Structs are basically, it's a package of multiple state variables combined together. Okay, so they're like, they are like an object in Java's JSON, right? So structs will basically combine 5 or 6 or, any number of different state variables together as a single object. We will be looking at each of these individually, right? But these are the different entities that go inside of every class definition, which is called a contract, right? And you can have multiple contracts defined in a single file, and together that will be called your smart contract file, right? Apart from this, apart from the contract definition itself, right, there are 2 other definitions that are defined as part of the Solidity language. One is an interface. If you've worked with object-oriented languages before, you should be fairly familiar with the concept of interfaces, right? Interfaces are just defining a shape or a structure for your class file, right? They tell that if a class file inherits from an interface, that all of the functions that have been described in the interface file will be implemented in your class file, right? So interface is just like an index or a shape, right? Or a structure, right? That defines that these will be the functions or the state variables or the structs or the events available inside of any class or any contract that implements this interface. Library is just like a contract, right? But has a different purpose. It has a different use case, right? So a contract is obviously used to trigger, to accept outside functions, the transactions that, that call functions of these contract, right? A library is basically a contract that is to be used by other contracts, right? So it's a way of distributing your code and making it, semantically much better, right? And so that you can split your code into multiple files. So if you have reusable code, right, you put that code as part of a library, which also ends up being a contract, but it's a contract that is used only by another contract and not by people from outside. All right, so let's look at those 5 elements that we talked about, right, that form the basis of any contract. First element is a state variable, right? A state variable, like I said, is any variable, right? An important thing to remember about Solidity is it's a statically typed language, right? What that means is every single variable or a function will need to have a type with it. When I say a type, I mean this little thing here, right? Uint, whether it's an integer or a string or an array or whatever, right? So there needs to be a type with every function or every variable that you define, right? And that's why it's called a statically typed language. All right, so what we are seeing is a very simple example of how you define a state variable. This is the simplest of thing, right? We looked at two things. We looked at this. So this is a very simple contract file, right? A contract file can be as simple as just these 4 lines of code. First thing we defined is one of the pragma directives. We said that the compiler versions that I'm supporting are greater than 4, right? And less than 7, correct? Then I'm saying that, here's my contract class, right? So I've defined my first contract class. I've called it simple storage. And inside of that, I've defined my first state variable, right? And because this is statically typed, every variable needs to have a type next to it, right? Before it essentially. And for this, I'm defining a type called uint. We will be looking at all of the different types that are supported inside of Solidity. Right, so the different types that we can support, right, all of our state variables, these are the different types that we can support in types of Solidity, inside of Solidity. Booleans, obviously the most obvious thing, right? So true and false, and you can do multiple operations on booleans, right? You can compare them, you can do equal, not equal to. Integers, obviously both signed and unsigned integers are supported. Fixed point numbers are supported, floating point numbers are not supported, right? Fixed point numbers means there is a fixed number of decimals fixed number of bits after the decimal, right? So a 2.5 is a fixed number, right? A fixed point number. So these are decimal numbers with fixed bits outside after the decimal number. All right. Address is another value type. This is another type that is supported. This is a specific new sort of thing that you've not looked at in other programming languages, right? So it's a new type that is created for Solidity. An address is a type that basically means that it is an Ethereum address, right? We know what Ethereum addresses are. We know that it's a public key. We know that it starts from 0x, right? It's a 20-byte long key that is used to identify every single address, right? So those addresses have a special type to them. They're called address, right? There are two types of addresses as types inside of Ethereum, right? So you can have a certain thing called let's say one address is called address, the other one could be called address payable. Okay, so two different types of addresses: simple addresses and address payables. The only difference between these two types is if you give any variable, any state variable, the type address payable, then only then can that variable accept Ether. All right. So you cannot send ethers to any variable or any contract that does not have the type address payable. Okay, so it's a condition set inside of Ethereum. It's important to understand the difference between address payable and address. Contract. So when you define contracts inside of the solve file, right, each of those contracts have their own type. So contract is again a special type. Each contract defines its own type. And that is important because Ethereum supports inheritance, which means I can import one contract inside of the other, right? And when I do that, I define a variable which refers to that particular imported contract using the type of that contract. When we look at some of the code, this will become a little more easier to understand, right? So just remember that contracts have their own type. And that's also one of the types that's supported. In before 0.5.0 in Ethereum, in Solidity, contracts were actually of the type address. So every contract, because it had its own address, the type of contracts was also address by default, right? Now with 0.5.0, this has changed, right? Contracts have their own type, but it can be it can be explicitly converted to the address type, right? So that is possible, but by default contracts have their own type. And then obviously the common things like fixed size byte arrays, right? So, and then dynamic size byte arrays. So if you define something like bytes 1, right, that's an array of 1 byte. Bytes 32 is an array of 32 bytes, right? Or you can just define bytes, which will mean that it will be a dynamic sized array based on how many bytes you put inside of it, right? And then there are enums, right? I talked about enums. Enums are defined something like this, right? Enum and then the name of it, right? And then you define an array, essentially all of the different values that the enum can take in an object. Okay. So yes, Suresh, that thing will get a little more clearer as we go towards looking at some of the actual codes for smart contracts. What do I mean by its own type, right? So to give you a very brief idea, when I define a contract like this, right? So simple storage becomes its type. So the name of the contract sort of becomes the type of the contract. All right. So now so we have looked at the value types, right? So these are again, so they're all just a combination of data types that are supported. Some of the other data types that are supported inside of Solidity are essentially structs. Remember I said that structs is a combination of different state variables. So this is how you define a struct. Like if you have a struct called funder, right? So then you can have different variables inside of it, right? And together they'll be called, so it's like defining an object in JavaScript, right? In JSON. So if you want to add, let's say if you want to access the value of address, right, you would write something like funder.address. Or if you want to access amount, you would write funder.amount, right? So that's how you define structs. Arrays are exactly what you would expect out of them, right? So they can either be fixed size or dynamic sized arrays, and you can define arrays of anything, right? So you can have any of those existing types that we looked at earlier, and you can have an array of that, right? So this, for example, is an example of looking at an array of UN32, right? So it's a fixed sized array, a 5 sized array, right, of a dynamic array of unsigned integers, right? So you can have an array of array as well. So nested arrays are also supported. Mapping is again a new type that is introduced inside of Solidity. Mapping is essentially, it's similar to a hash lookup, but it has very little similarity, and it ends at the only similarity instead inside of a hash lookup is how you understand it. So a mapping looks like this, right? So you would define a mapping between an address type and an unsigned integer type, right? And you would call the mapping balances, right? So what that would mean is it'll you can have it's like defining a hash lookup where you have a key and a value, right? So for every key you will define a certain value. The key will be of the type address, the value will be of the type unsigned integer, right? So your balances will essentially be like a hash table. But this is where the difference ends, right? Because in terms of how it's implemented, a mapping is not iterable, right? So there is no indexing, so you cannot just list out all of the balances. So that's a huge difference, because if you add like 10 values inside of balances, and you have the keys for each of them, and then you have the values for each of them, you can't just do like balances dot list all, right? Which is what you would do with hash lookup tables, or get the values of all of the balances. So that's not possible in with mappings. So the only way to do that is you will have to keep track of all of the IDs that you've put as keys for balances separately, right? And then you will have to loop through each of those IDs and fetch the balances for each of those IDs. The reason that happens is because the keys themselves are never saved inside of balances, inside of these mappings, right? A hash of those keys are saved. That's just the design of the EVM. All right. Give me 1 second. So the next thing to look at is the fact that these state variables, we will be looking at the different visibility and the types of these state variables. Okay. So while you were looking at some of the examples, right, you were looking at things like I defined a variable and then I said something like memory ahead of it, right? Or I said something like public ahead of it. So these are, this is where you define what the visibility criteria is and what is the type of that particular variable. So in terms of visibility, a state variable can either be public, or it can be internal, or it can be private. We will look at the differences between public, internal, and private when we talk about functions, because functions have the same types of visibilities also. So when you define functions, just like you've defined the state variables, right, you will be deciding their visibility. And we will look at the different types of visibilities that are available when we talk about functions. All right. So then there is a type of state variable called a constant state variable, right? So to define a constant state variable, all you will do is when you define the type of it, in front of it, you'll put the type, which will be constant, and then the name, and then constant variables obviously have to be initialized, right? Currently, so constant support is something that was added recently as part of 0.5.0, and it's still not completely supported. So the only two types that are currently supported for constant variables are, the integer, so the bytes types, and the string type. All right, so now let's start looking at functions, right? So that's element number 2 that goes inside of a smart contract. First was obviously variables, and then functions. Again, functions have a very similar type of how you would define them. There is the function. This is the syntax, right? So you have the function and the name, the parameters you will pass to it, right? This is where you will define the visibility of it. So it could be one of these values. This is where after that you will define, the type of the function that it is, right? Remember I told that one of the elements that goes inside is the function modifiers. This is where you will define the modifiers. And then finally the return values, right? What are the values that it will return, right? So this is the syntax for functions. The name, parameters, and the values that it will return, correct? So this is the core function syntax, very similar to how you would work with any object oriented language, right? Now let's look at the different types that are available, right? Remember, as part of state variables, we looked at it had 3 different type options, visibility options: public, internal, and private, right? Functions have one additional option, which is external. So let's look at all 4 of them. External means that if a function is an external function, then it is a function that is only accessible from outside the contracts, right? Which means that if I define a function XYZ to be external, then only other EOA accounts, right, externally owned accounts, can initiate transactions to execute that function. Any other function inside of the file cannot call that function. All right. A public function is a function, it's like external functions, but it can also be accessed from inside of the file as well, right? So it can both, so an internal function can also call a public function, and an external function can also call a public function. All right. But if it's an external function, then it can only be called from outside. Internal functions cannot access it. All right. Now an internal function is something which can be accessed by the functions inside of the file, or from other smart contracts that are derived from this smart contract. What I mean is, I told you smart contracts support inheritance, right? So you can import a smart contract inside another smart contract. When you do that, right, the imported smart contract can also call these internal functions, right? But any externally owned account cannot initiate a transaction which will call an internal function. All right. Private functions are just like internal functions. The only difference is private functions are specific to that particular smart contract. So even derived contracts cannot access private functions. All right. An important thing to note is the terms internal and private can sometimes be confusing, right? When I say a private function, it doesn't mean that the function cannot be viewed by somebody when you're looking at a blockchain from outside. Blockchain public data is public, right? So these visibility parameters only decide how these functions can be accessed through code, right, or through an external transaction, right? A private function's results and its data will also be public, right? It's just that how it will be accessed through code or through external transactions is what is decided by these visibility parameters. Now let's look at the different function types, right? So there are 4 different types of functions that could be included inside of any smart contract. The first one is called a view function. A view function basically tells that, so if you define a function as a view function, right, what you're saying is this function will not modify any state, right? So if you let's say, for example, you defined a state variable, right? Like right now we defined a state variable called text, right? So this view function will only allow you to access the value of text, but you cannot change the values of any of the state variables, right? So view functions are generally for fetching data, right? So they give a promise. So inside of a view function, you cannot change any data. Okay. A pure function is similar to a view function, but it's one more step ahead of it, where it says that not only will it not write to the state, it will also not read from the state. So it has zero access to the state variables. A pure function is generally there for semantics, so let's say inside of your code, if you want to split your code and you want to run some of your computations inside of another function, so they're basically helping functions available inside of your code, right, where neither is it accessing any of the state nor is it changing any of the state, right? So pure functions are actually very popularly used inside of the code, right, but they're mostly helper functions. All right. A payable function is a special type of function that is available. So if remember I said that there is a type called address payable. Similarly, there is a function called payable. Only if a function is payable can you actually send ethers to it. All right. So if let's say if you're initiating a transaction to a smart contract and you're trying to send, there's a function there called accept money, right? And you're trying to send some ether to that accept money function. If that function is not defined as payable, right, it will reject that transaction and your ether will come back to your account. All right. And then there is a concept of a fallback function. This is a special function. Every smart contract can only have one such function. All right. And a fallback function is essentially a function with no name, right? So it's just function and then the parenthesis, right? So a fallback function is executed when if somebody tries to access your smart contract, right, and none of the function parameters match with any of the existing definitions, the fallback function will be executed. Also, if I try to access a smart contract without calling any function and just randomly sending some ether to that function, to that smart contract, right, the whole ether process is handled by the fallback smart contract. Right, so the fallback function's duty is to handle two things. One, it is obviously supposed to handle the fallback, which is when it doesn't match, the request doesn't match any of the defined functions in the program. Or two, if there is a transaction that is coming in with just ether, which is a value transfer transaction. Remember I told you there is a type of transaction called a value transfer transaction. So if somebody is just trying to send ethers to a smart contract, right, that ether is essentially added to the balance of the smart contract by the fallback function. Yeah, it's sort of like the default, right? It is like the default. It is where your values will, so if nothing is matched, this is where it'll go, right? The scope for fallback or the scope in general? Oh, the scope for the fallback is for the entire smart contract, right? For that solve file, right, which you define, within which you can have multiple contract classes, right? So each contract class will have its own fallback. No, you cannot. So you cannot just call a fallback function. It has no name, so it cannot be referred to. All right. So now the next thing we will be looking at is function modifiers. Right. Function modifiers, like I said, is a new thing introduced in Solidity. It's a special type of function, right? And this is how you define a modifier, right? So it starts with a keyword called modifier, and then the name of the modifier, and then some code inside of it. And it always ends with this underscore, right? This underscore says that this is where the code execution returns to the definition of the function. So it's sort of like a return statement, right? So it's a shortcut for a return statement. An underscore means that the execution of modifier ends here, and then the control should now pass to where this function was called. All right. The reason we have modifiers is you include these modifiers as part of your function definitions, right, to control the access or something else that you want to control, inside of the functions. So for example, like this is a modifier called only owner, right? Now, as part of my function definition, right, if I were to define a function called function Akash with some parameters, which is an external function, right, and a view function, and then the modifier I say only owner, right, that means that this particular external function, which is a view function, can only be accessed by the owner of the function, right? So only if my incoming transaction succeeds in passing this condition that is defined in the modifier, right, will it be able to enter the function, right? So that is how you can define. So owner, as in, this is how you define, right? So this is the code that I've defined for defining who is the owner. Okay, so there are a lot of predefined global variables available inside of Solidity that gives you access to the context. Remember I said it operates in limited context, right? So there are certain level of context that every transaction has. For example, message.sender is one of the global variables. We will be looking at some of the other global variables also, but message.sender is one global variable, right? What this means is this is the incoming message and the sender of the message, right? So the sender, as long as the sender of the, so basically what we're saying is we need the sender of the message to be the owner, and owner is a variable that we might have saved earlier in part of the contract. All right. So as long as the sender of the message matches the owner, and this message.sender is basically the address of the transaction initiator. Yes, the who deploys it is the owner. So at the time of deployment, we would have initialized this owner variable with the address of the deployer, right? And now at the time of access, we are verifying that, you know, the incoming transaction is matching the address of who deployed it, right? And that is what is controlling the access for, let's say, for this particular function. All right. Now let's look at the fourth element inside of, you know, our contract classes, which is events, right? See, it's been pretty easy, right? These are simple things, right? We've already looked at fourth of the fifth of the total 5 elements that go inside of contract classes, and that's pretty much what it is. So the next thing is events, right? We've looked at events. We know that events, you know, are so they are an element that you can trigger, you know, that allows these logs to be generated. These logs are stored inside of the blockchain, right? The clients can subscribe to these events, and they can listen to when certain things happen as part of transaction execution. The logs are associated with the address of the contract. Okay, they are stored in a special location inside of the blockchain, and they are always accessible as long as the block is accessible. This might no longer be the case in the future. As part of Ethereum 2.0, one of the suggestions that have come in is the logs will be truncated or deleted after a certain number of blocks. And the responsibility of maintaining or sustaining those logs will go out to the other networks that are built on top of Ethereum. But anyways, that's a slightly tangent topic. So yeah, events trigger logs, right? Logs are saved and accessible. There is an attribute inside of events called indexed. When you add that attribute to any event trigger, you know, that particular indexed trigger becomes a topic for that particular event. Okay, and you can filter through, when you're listening to the events, you can filter to events based on which topics you want to listen to. All right, so that's an additional functionality that's available. So you can listen to events only of certain topics, right? Instead of listening to all of the events for a contract. So we know that when a transaction completes, okay, whether it's successful or not, it produces a transaction receipt, right? This receipt contains the log entries that were generated as part of executing the contract, right? Obviously, logs are only generated if the transaction has these events. Okay, only if a transaction execution emits events will the log entries be generated. And these events are very useful for these clients or any other applications that we build, so that they can watch these events and do something on the user interface. This is how you essentially define the events. Okay, so if we have a contract which is, let's say, faucet, right? This is an event that we've defined. We've said that the event is called withdrawal. All right, and there is, you know, 2 variables inside of that event, right? So there are 2 state variables inside of the event, right? One of them is an address variable, and then we've indexed it. So that means that, you know, the variable 2 is now you know, it's indexed, so it can be used as a topic, right? So when I'm listening to this withdrawal event, I can filter it by the event 2, right? So if I want to filter it based on who it was sent to, so listener can filter it based on, whether it was addressed to me or not, right? So that's how you've essentially defined indexes for particular variables inside of event, and anything that's described as an index can be used as a topic. There is a limit to it. You can only at max define 3 indexes inside of every event. Okay, so you can have any number of variables inside of an event, but only 3 of them can be indexes. All right. So what you looked at here was a definition of an event, but this did not trigger an event. So now as part of your smart contracts, right, you trigger those events using the emit keyword. All right. So in your smart contract, let's say we have a function called withdraw, right, which is a public function. Inside of that function, what we're saying is after the function has been executed, emit the withdrawal event, which has been defined already, right? So we emit the withdrawal event and we pass the values, right? So this is where the event will be triggered and the logs will be generated. Right? So some questions obviously do arise, right? How do we set up our contract to emit events, right? And then how do we see the results of a transaction, right? Where do we catch these events, right? Who catches these events? If they're generated, how do they look like? And all sorts of things obviously come to our mind. So the thing to remember right now is when these events are executed, emitted, they are caught by the client. A client can either listen to the live events or they can also go and fetch some of the historic events. And obviously we know that the clients interact with the node using a library called web3.js. So web3.js has functions that allow us to fetch events or listen to events. All right. So we will be looking at web3.js in the next session, and that is where we will see how these events are generated. We will capture some of the logs, right? And we might use some of these logs to, to decide the flow of our application. All right. Now let's look at some of the globally accessed variables, right? We looked at message.sender as one variable that showed up in the code earlier. And I said there are multiple other globally available variables as part of Solidity, right? So there are some built-in functions that are available. You don't need to know each of them right now, right? One important function that you will most definitely use if you're using a smart contract will be self-destruct. Self-destruct is a function that you code as part of any smart contract to delete the smart contract, right? So when you remember, I said that smart contracts cannot be updated, but they can be deleted. So if you want to delete a smart contract, right, the delete code. So you can code a function inside of a smart contract called delete, and inside of that you can call this function called self-destruct, right, which will instruct the EVM to delete the code that is existing at that particular contract address. Remember one thing, when you self-destruct a smart contract, it only deletes the code. The contract address is still there inside of Ethereum, right? So now once you've deleted the smart contract, if you try to access any of the functions, obviously it'll give you an error because there is no code existing. But if you end up sending some ether to that smart contract, right, as a value transfer transaction, right, that will still happen, but that ether will be lost forever because there is no code controlling that smart contract. So you basically sent your ether to an address which is not controlled by anybody, right? It's a dead address. Your ether is now lost. So that's why most people don't self-destruct smart contracts. You use a concept called disabling smart contracts, which is not supported directly, but it's a pattern that's used regularly, where you have a code inside or you have a switch inside of your smart contract, right, which you trigger through a transaction, which then changes all of the function code to not allow anything after that. Right? It's like a kill switch you build inside of your code. All right. There is the this variable, right? So the this keyword will essentially give you the address of the currently executing contract. There is also a now keyword, which will give you the timestamp of the current block. Remember, smart contracts execute in limited context, right? So they do not have access to the current timestamp because they do not have access to the hardware machine, right? So they do not have access to the clock of your machine, right? So the only way you can get the current time inside of the Solidity interface is you call this variable called now, which will essentially fetch the timestamp of the last block, the current block essentially, right? and that might not necessarily be the current time. It might actually be 5 minutes before now, but that's the only option you have. All right. And then there are, some contracts, some global variables available for messages, right, or transactions, right? Message.sender, we have looked at this. It will give you the address of the originating transaction, right? An important point to remember is we know that I can initiate a transaction from an EOA account, right, to a contract address. The contract address can then call another contract address. When that happens, the message.sender that will go from my account to the contract first contract address will be my address, right, because I sent it. Then when that contract address accesses the next contract address, the second contract address will see the message of sender as the first contract address and not my address. I hope that's clear with you guys, right? Because it's two hops, right? So the last hop will see the address of the previous hop and not the original sender. So the value of message.sender changes, right, based on who is then redirecting that transaction to the next entity. Right, and similar to message.sender, the value of message.value will also change. Okay, it's basically the number of ethers we send, as part of where. Remember, I told you that when we send transactions, we have to send some amount of gas, right? And that is sent as part of that message.value. Or if you are just doing a value transfer, obviously even then you have to send message.value, right? So when you send, let's say 100 ethers or 100 gas value to a first contract, right, and that contract has to access some second contract, the first contract decides how much ether it wants to send to the second contract for it to be able to execute its whole gas function, right, and then whatever is remaining is sent back, right. So the message.value and message.sender changes its value depending on the hops. There is a different type of transaction available where you can access hop based contracts. You can access the second or the third contract in the hop with them all seeing the original message sender or the original message value, and that is a different type of transaction. It's called a delegate call. We will be looking at that type of transaction also today, right? So that transaction is used when you're accessing something like a library, right? So if a smart contract is accessing code from a library, right, then obviously it doesn't want to change the message.sender for that library, right? Because it only wants to fetch the code from that library and not send it its own messaging address. So in that case, it uses a delegate call, right, wherein the message.sender is actually the address of the original sender. All right. So Sheikh is asking, can we reuse the address for new contract or new code at that address? No, right? You cannot. If you have an address for a particular contract, it's gone forever. You can't put anything else on it again. If you even delete that particular code, you cannot now put some new code on that same address. That's not possible. Right? Because the only way you install smart contracts is you install it at a 0x00 address, right, which auto assigns an address to the smart contract. So you can't define what address you want to install your smart contracts on. It is automatically calculated based on an algorithm defined in EVM. All right. So the next thing now is message. Okay, so there are some more other things. So message.data is just the payload that comes as part of your as part of your transaction. Message.sig is another global variable available. This is not used as often. Message.data is fairly often used. Right. So this is where remember I told you that when a smart contract calls another smart contract, the value of message changes, right? But except for a function called delegate call, within which the value of the message context does not change, right? Then there are the transaction context, right? Inside of the transaction context, again, we're just discussing all the global variables that are available. Okay, remember that. So another context that is available is, the incoming transactions gas price or the incoming transactions origin, right? So the incoming transactions gas price will give you, so when you send a transaction, you set a gas price on it, right? So as part of your code, if you want to fetch what was the gas price that the sender has set on the transaction, you can fetch it using this particular keyword called tx.gasprice, right? Or if you want to fetch who is the original transaction initiator, right, and the address of that initiator, you can fetch it using that. Similarly, there are contexts for fetching data about blocks. Okay, so these are global variables for fetching data about block. So inside of your code, if you want to fetch what is the hash of a particular block number, you can use this function, right? Or if you want to just fetch, the Coinbase for this particular block, right, which is the address of the current fees and the reward for that whole block, you can fetch it like this, or you can fetch the difficulty of the block, or you can fetch the gas limit or the block number or the timestamp of the block, which is similar to using the now function, right? So these are some of the global variables available for fetching data about blocks. And then finally, there are also context available about addresses, right? So let's say you have a particular address, like we said, message.sender, which will give you the address of the sender, right? So that address itself will have other members available inside of that address. So you can fetch the balance of an address using address.balance, right? Or you can transfer some amount to an address using address.transfer, right? And putting the amount here. Address.send is very similar to transfer. The only difference is how they return, right? If there is an error, address.transfer will return with an error. If there is an error in address.send, it will return with a false, right? So this will break the transaction. This will give you an opportunity to catch the error and then do something about it, right? This is how you do it, right? So let's say you have an address which is a payable, right, and you define it as this. Okay, so now and then you have another address which is the address of this. Remember that this variable will give you the address of your current smart contract, right? So you have two addresses, and then you're doing address.balance, which will give you the balance of your smart contract. Okay, and then you also have the particular address that you selected here, and then you're transferring 10V to it. All right. Some more other variables that are available, functions that are available as part of the address variable, that are address.call, address.staticCall, address.delegateCall, right? This is what I was talking about when I said that there is a different type of function that you can use to contact other smart contracts. So all of these three variables are essentially low-level functions that you can use to contact other smart contracts, right? Remember I said there's a limited ability for smart contracts to connect to each other, right? This is how you can contact. This is one way, but the not suggested way for contacting smart contracts is you can so basically an address.call will send this payload to a smart contract available at this address. An address.static call is similar to a call function. The only difference is it guarantees that the static call will only be a read function. It will not change the state in any way in the receiver contract. All right. Address.delegate call again is similar to the call. The only difference is in this case, the message context remains the same as the original sender, right? Because in the regular call function, it will change the message context to the sender and the value of the contract and not the original sender. So apart from that, there are also a lot of different units that are available inside of Solidity. For example, if you want to just define something as way or ether, right, you can use terms like way or ether as a suffix to that number. So let's say if you want to say something is 1 ether, you can just say 1 space ether, and that sort of predefines it as 1 ether. Similarly, you have units like seconds, minutes, hours, days, which you can use as suffix to certain numbers to defining time units. All right. So now that we have looked at all of the 5 different things that go inside of the smart contract, right? Now let's look at actually defining a smart contract. So as part of the smart contract function, right, the contract class, this is how you define it. It will start with a constructor, obviously, right? A constructor is not mandatory. If you want, you can have it, but more often than not, you will obviously have a constructor as part of your smart contract, right? A constructor is executed when the smart contract is being deployed, and then it is removed from the smart contract, right? So it can only be run once, right? When the smart contract has been deployed. So this is where you will set all of the initial values for your smart contract as part of the deployment process, right? This is the syntax for defining a constructor. You would just say constructor, pass some variables to it, right? Call it a public function, and then you will put all of the logic inside here. Right? Similarly, just like the constructor definition, there is also another function. Like I said, we've looked at this earlier. We said there's a self-destruct function, right? This is also something that you will mostly have inside of your smart contract, right? There are two things that you must always have inside of any smart contract. One is, the contract constructor itself, right? And then a self-destruct function if at any point you want to kill that smart contract, right? So you will define a function like a kill function, and inside of that you will have the self-destruct function being called. There is an important reason for the self-destruct function, the address that you pass to this, right? This is the address where all of the balance ether of your smart contract will be transferred to when you kill this function, so that that ether is not lost, right? So if your smart contract, let's say, had a balance of 50 ethers, and you decided to kill it, right? Those 50 ethers will be transferred to this recipient address, which is defined when you coded your smart contract. All right. So this is a sort of an example of one very simple smart contract, right? We have the pragma directive. Self-destruct will happen, Suresh, when you call it, right? So it'll be visible. It'll be easy to understand from this particular code here, right? So we have the pragma directive, which is where we define which version of Solidity we're using. The contract is called faucet, right? There's only one contract class inside of this contract file. It's a solve file, right? So we have defined one state variable called owner of the type address. This owner is defined to be the message.sender as inside of the constructor, right? So when this contract is deployed, at that point, whoever is deploying this contract, right, will be the message.sender, and that will be set as the owner. And then that can never be changed, right? Because there is no other function here which allows to change the owner, right? So we have defined the owner to be the message.sender as part of the constructor, which is a one-time process, right? And then what we are doing is we are allowing that owner to destroy this function, right? How are we doing this? We're saying there is a function called destroy. So if somebody else calls this destroy function, what will happen is it will check if the message.sender, whoever is calling this function, is the owner or not. If he's not the owner, right, this transaction will not go further, right? And it will revert with an error. But if he is the owner, then it will allow him to self-destruct, right? So the owner at his choice can at any point call the destroy function because he's coded it, right? And that function allows only him to be capable of doing the function call for that particular function, right? As we have looked earlier, we could have also, right, created a modifier of calling, modifier like only owner, and put that as part of the function definition, right? So modifiers are generally used so that you don't have to put these require calls everywhere inside of every function and have repetitive code, right? You can define a modifier like only owner once and then put it inside of every function of your smart contract. Now let's quickly look at inheritance, right? I have been saying that Solidity supports inheritance, which means that it can import other smart contracts, right? So the basic inheritance that is supported is coded in this way, right? The first thing I will do is at the top of the solve file, I will import this particular base parent, the base smart contract, which is called parent, right? And then I have defined a new smart contract called child, right? And I've said that child is parent, which means that child inherits from parent. So all of the functions and state variables defined inside of parent will be available inside of the child definition, right? So that's the basic concept of inheritance, and that is supported inside of Solidity. So this is how we would do it, right? Here's an example of the code. first, the first thing that we will do is we'll define a contract called, let's say, owned, right, which is the base contract. So inside of the base contract, we've defined obviously the constructor, and then we've defined a modifier. All right. Now we will define, a child contract, and then we would say that the child contract is owned, which means it is inheriting the owned contract, which is the base contract, right? And because we have done that, you will see that inside of this function definition of the child contract, right, I can use the only owner modifier, which is actually coming from the parent contract, which is here, right? So the base contract, so this is to prove the fact that the definitions and the functions and the address, the state variables inside of the parent or the base contract can be used inside of the inherited contract, right, or the child contract. So what we have done is the file, the function that we saw here, right, the example for contract construction and destruction, we have sort of converted that into a more semantically perfect code with having two contracts that were inheriting each other, right, or having one base contract and then that being inherited by the child contract, right, and split the code in two files, right. And this is now taking it further. So this is the next level of inheritance, where we have defined the third contract, faucet, which is inheriting this particular contract, right? So owned is the base contract, right, which is inherited by Mar'10, and then faucet is the third contract which is inheriting Mar'10, right? So everything inside of owned is also available to faucet, right, because that's available to Mar'10 and Mar'10 is available to faucet, right? So you can go on multiple levels. You can have the whole hierarchy of inheritance, and all of the functions will be available in the global scope for the lowest level child function, right, the lowest level child class. All right. So yeah, so that's the idea of inheritance and the basic example. I'm sure most people are already available with at least the basics of this, right? Now let's look at another important concept inside of Solidity, which is error handling, right? It is very important to have error handling inside of this, because remember, error equals money inside of Solidity or EVM, right? So what you need to do is you need to check for errors, and you need to make sure that you terminate your contract execution, or you revert your contract execution every time there is an error, right? So there are three main types of error handling functions available inside of Solidity. They're called assert, require, and revert. All right. So let's look at that one by one, right? Assert and require functions go together, right? Well, actually all three of them sort of go together, but assert and require are very similar in the sense that they solve the same purpose, right? They set certain conditions that have to be be successfully adhered to for the execution to move forward, right? So generally this is the convention that you must remember, that if you want to check the internal conditions of the network of your particular contract, right? So let's say if you want to check some of your local variables are set to the right values or not, right? If you want to check some of your variables are defined or not, for example. So if you want to check internal conditions, you check that with an assert statement, right? So as part of your function definition, at the top you will first make sure that, okay, I will assert that this value equals this happens, this value equals this, and and only when all of these asserts are successful, right, then I'm going to go ahead and actually execute my function. Similarly, if you want to test for inputs, right, a user is sending a certain input, and you want to make sure that that the ID has been sent by the user, that the ID is a length that is required by your transaction, right, or some other value is sent by the user or not, right, or in some cases that a certain value is not sent by the user, right? So you can check all of your inputs for every transaction using the require statements. So in this way, assert and require sort of form the two statements with which you can check, right, the right execution condition for your transaction before you actually start the execution. Remember, checking for the right state, the right as a results for using assert and require will also consume gas. It's not that those are free. but at least it'll give you an opportunity. So it's, it's a fine balance between having how many assert and require statements inside of your code, and what will be the cost of not having them, and your contract fails, right? And you end up spending a lot more, right? So as part of as part of being a contract designer, this is something that you must take care of, as to how many assert and require statements you want to have, which will cost you gas, which will be an overhead, but it will save you more money that could be cost in, when there might be a bigger mistake. Right, so this is how you define the require statements. We've been looking at require statements already, right? There is one other thing that you can add to a require statement, right? There's only one other attribute that you can add to it, which is a string, which is where you can define the statement or the message that will be returned to the user, the transaction initiator, right? When the require statement fails, when it reverts, right? So if this fails, right, you want to tell the initiator that the contract can only be called by its owner, right? And that is what you're doing as part of the require statement. Require statements were not supported. So the messages and require statements have only come as part of 0.5.0. Before that, they weren't supported. All right. And then the other thing to remember is the revert functions, right? So the revert functions will essentially stop the execution, and it will change the state. So everything that has changed as part of your contract execution, right? So for example, your contract was something like x is equal to 5, y is equal to 2, right? X plus y is some value, right? And then you take x into y, right? So the contract execution has come to level 3, step 3, where it is done x plus y equal to some value, right? And while doing x into y, it failed. Okay, so you call the revert function. What that will do is all of the values that were changed before this error happened, they will be reverted back to the original state, right? And nothing will be updated on the blockchain, right? So a revert function halts execution, and it reverts the state of all of the variables to the original state when the contract was not, when the transaction had not initiated. All right. So so this is what you would generally do, right? So very regularly, as part of your contract definition, you will have these require statements, right? And only when these require statements pass will the code below it will be executed. All right. And like I was saying, it's important to make a choice between the amount of gas that will be consumed for running these error checking code, which is your require and assert statement, right? And the risk of spending more gas if you make a bigger error which is not caught by these error checking codes, right? So you have to make that choice. All right. So now let's move on to one other important factor, which is calling other contracts, right? We've looked at these three functions, right? They're available as part of the address object, right? We can either send, call, and delegate call, right? We've briefly looked at these functions. So these are three available low-level functions that you can use to call other contracts. This is apart from inheriting contracts, right? So when you inherit a contract, its code is available for to be executed inside of your own code itself, right? But there will be times where obviously you're not inheriting a contract, but as part of your code execution, you want to fetch data from some other smart contract which belongs to somebody else, right? So at that point, you will be calling that contract, and you will be fetching data from there. All right. So that's an important point. I think let me see if this sort of needs to be looked at right now. All right. So the thing that you must note here quickly is, as part of defining a contract, right? So what I've done is, so this is how, when I said that smart contracts have their own types, this is an example of looking at how smart contracts have their own type, right? So I am basically initiating a new instance of a smart contract, right, which is called faucet, which is defined in some other file which you don't see here in this code, right? But as part of doing that, what I'm doing is I'm initiating a state variable of the type faucet, right, which is basically a type of a smart contract, right? and then I'm initiating this new variable by the name underscore faucet, and I'm assigning it a new instance of this faucet smart contract. Right. So this is one way how you can basically create new instances of smart contracts, right, that you have not inherited from, but you essentially have the whole code for that smart contract available. All right. So as long as you know the exact code for that other smart contract, you can create a new instance of that smart contract inside of your contract, and then use that to access all of the functions inside of the smart contract. Right. So this is, and you can then obviously call that smart contract. So this is one way of doing it, where along with initializing a new instance of that smart contract, you're also passing it a value, right, which is some amount of ethers, right? And this little parenthesis at the end, which is blank, is basically running its constructor method with no variables and with no arguments, right? So this is how you've essentially initialized a new instance of faucet smart contract and started it with a value of 0.5 ethers. These values sent from your current smart contracts balance. All right. Right. So this is just looking at that same thing again, right? Right. I think this is sort of covered, right? Let me see. All right. So this is another way of adding or accessing another smart contract, right? Which is, so we've looked at a way of defining a new smart contract using the variable new, right? Which is what we have done here, right? One final way of how you can access a smart contract from another smart contract is by essentially, casting its address. So if you know the address of, the contract that you want to use, right, which is, obviously every smart contract has an address, right? So what I've done here as part of this contract here is token is my new contract, right? I've imported the code for faucet, which is the contract that I want to use, right? So what I'm going to do is faucet is the code for this. So this is the file of the code for the contract that I want to use, right? And as part of constructing my token contract, I am passing it the address of the faucet token of the faucet contract, right? Now this address can be used to initialize the faucet contract. All right. So this faucet contract can be initialized using, calling the function of the faucet contract, the constructor of the faucet contract, right, and passing it the address of where it is deployed on the network, right? So some people might ask, if I can just inherit smart contracts, right? What is the purpose of doing all of these different ways of accessing smart contracts, right? So remember one thing. This token smart contract is inheriting from the Mar'10 smart contract, because both of these smart contracts are yet to be deployed onto the blockchain, and they will be deployed now as part of deploying it together, right? But obviously there will be times where I have already deployed a contract like faucet, right? And I want to use some functions inside of that already deployed contract, right? So in that case, what I will do is, so this is one way of using already deployed contracts, right? So you would have the code for the contract that you deployed. You will import that code, right? And you will fetch the contract using that code and the address that where your contract was deployed, right? And that way then you can run the functions from this contract on the contract which is deployed on the network. Right. So these are some examples of how you could essentially access contracts using some low level functions like call and delegate call, right? But these functions are not, so it's always advisable to not use these low level functions because they're very risky. Because the EVM does not check, or the compiler does not check for the validity of these calls. These are direct opcode calls, right? So any sort of errors could happen as part of using these calls, and that will be risky. So it's not advisable. These are like the last case efforts that you would use. Right. Now lastly, the thing that we must all remember is, obviously, it uses a lot of gas, right? All transactions use a lot of gas. All right, guys, we've just crossed 10 o'clock, right? Which is the time that we end today. Um, do you guys want to stretch this for another 15 minutes? And maybe, so we will definitely not have enough time to cover web3.js today, but we can definitely finish up, Solidity. We've almost looked at everything that we wanted to look at Solidity. We just have to look at some of the things related to the tips and tricks of, how you save some of the gas and what are the tactics that you must use to save gas as part of defining your contracts. And then we will end it there. So is everybody okay with spending another 15 minutes? Okay, all right. Cool. So what I was saying is, obviously we know that gas is critical, and Ethereum or EVM works in a sense where it's very tightly coupled to gas execution, right? So what will happen in terms of cases where you try to run a transaction, right, but you've not passed enough gas to that transaction. At that point, at the stage where the EVM runs out of all the gas that you have passed, right, it will trigger an out of gas exception, right, which is generally called an OOG exception, and your state will be reverted, right? And we know state revert is basically going back to the original state, right? But all of the gas that has already been consumed, right, as part of reaching that exception, will not be refunded back. It will be taken by the miner because he spent resources in running your error transaction, right? So the thing to remember is, because transactions are obviously triggered by end users, right, and they will be the ones who will be paying or bearing the cost of your mistakes, right? There is a huge disincentive for people to run smart contracts, or use applications running smart contracts that can cost a lot of money because of errors, right? So as a programmer, you have to be very careful in terms of how you design smart contracts, especially on a blockchain like Ethereum, so that your gas costs are essentially very, very minimal, or the lowest possible, right? So here are some of the things that you must take care of as best practices to reduce your gas cost, right? As much as possible, as part of your code, avoid dynamically sized arrays. Okay, the reason for that is, when you define an array to be dynamic sized, right, your Ethereum virtual machine reserves, right, the maximum possible size for you, right? So even if you think you're using a dynamically sized array, right, what is happening is, in the memory space, in the storage space, you're actually reserving the entire disk space for you, the entire word length for you, right? So but and that has to be done, because although you might think of it as dynamic, the system needs to know that it can cater to all of your dynamic needs to the maximum possible level, and that's why it reserves that memory space for you, right? And that will cost you a lot of gas. So dynamically sized arrays are always more expensive versus static arrays, right? So if you know, or if you have a way of figuring out the maximum length, or the most equitable length for your arrays, always work with static arrays and don't go with dynamic arrays. All right. Also, as much as possible, avoid calls to other smart contracts. All right. Inheriting contracts is okay, because those are not external calls, right? They're just basically jumps inside of the stack machine, or references. But any external calls to other smart contracts also cost a considerable amount of gas, right? It also puts you at risk, where other smart contracts might not have been executed as good as you might think, and because of their mistakes, your users might end up paying more, right, or end up having a bad experience, right? So to avoid those risks, expose yourself to external smart contracts as less as possible, right? The other thing to remember, as part of running your transactions, right, as a client that you will build, or an application that you will build, which will access smart contracts, right, if you make a mistake in sending less gas for that transaction, right, there will be an error, right, out of gas error, right, and then it will have to be retried with an increased amount of gas. That will happen, that will make two things to happen, right? One, it will give your end user a very bad user experience, because he will have to wait for your mistake. Two, right, a considerable amount of money would have been lost in that process, right? Because that gas would have been consumed and it will have been lost, right? So you will waste money and you will, create a bad user experience. Both of these things are, extremely avoidable. So what you need to do as part of running contract transactions is, always estimate the amount of gas your transactions will consume. Okay, so there is a function that is exposed by Web3, right, which is the web3.js library. That function lets you, give out an estimate of how much gas would be consumed as part of your transaction execution. All right, and always make sure that you're sending out gas which is greater than this estimate, right? So that ways you will reduce. Again, it's not a guarantee because this is an estimate and sometimes it'll be wrong, right? But it reduces the risk to the lowest possible extent of running out of gas as part of your transactions, right? So estimating gas is very important. Also, another important thing is to get the gas price of the network, right? The gas price of the network is essentially, it's an aggregate of what is the current gas price running. Remember, you have to set a gas price for your transactions, right? The network doesn't really set a gas price for transactions, but obviously there is an estimate at which most miners are currently accepting transactions, right? So an ETH.get gas price will give you like the estimate of, at what price should you be pricing your gas consumption as part of your transaction proposal, so that the miners will be able to accept it. Because if you price your proposals too low, your transactions will be confirmed very slowly, or they'll be picked up very late. Or if you're pricing too high, right, then you're risking the chance of paying much more than you should have, right? So both of these things are not good. So as part of your application design, you must always make very intelligent choices in terms of what gas prices you're sending your transaction at, right, and what gas amounts you're sending it at, right? Both of these are driven by two APIs, which is the get gas price APIs, right, and the APIs for estimating the amount of gas consumption, right? So most application developers using smart contracts would build some sort of services which will constantly be calculating the most efficient gas price and gas amounts, right, using these two APIs, right, and plug those into the contract requests that are sent. Right. All right. So those were the most important things that we had to look at, in terms of Solidity, right? Next, what we will be doing as part of session 5, right, which will be the last of the sessions that we do for Ethereum, is look at the client side of things, right? So we will be now building an actual smart contract from scratch using Solidity as a language, right? Once we have built a smart contract, we will be deploying it to an Ethereum network. Right? We will be deploying it to a private Ethereum network that we had set in session 4, right? Last time, session 3, right? Using Geth. So we will use that same network. We will deploy the smart contracts on top of that network, and then we will be using Web3.js into a simple UI, user interface application, right? And fetch those smart contracts and display values on our application, right? So that will be that simple thing that we do, as part of the next 2 hours that we spend. I think that's going to be scheduled on Thursday, right? Is there any questions based on what we have looked at today? All right. So it looks like we are out of questions, or we are out of all of the energies. It's almost 10:15. So we're going to give it an end today. Give it some rest today. I know this was a lot to take in. Theories with programming languages are always very heavy on the mind, right? So what I would advise is to go to the read the docs, link for Solidity, and go through some of the docs there. Very well described. If you've got any questions, you know how to get in touch with me or the upGrad team. And all right, thanks a lot, guys. I'll see you guys again on the next session. Right, till then, keep trying, keep experimenting with Ethereum, and spend as much time as possible, running actual programs and actual test cases that you find on the internet. All right. Good night, guys. Thank you.